Verge-Project, WP5, Demonstration 2.3, Smart Micro-orchestration in Disaggregated Softwareized RAN Elements. Use Case 2. This demonstrator focuses on smart city scenarios involving tram lines, pedestrians, and vehicles. The goal is to provide a predictive reconfiguration of the RAN resources through an artificial intelligence probabilistic forecasting model. In addition, a reactive reconfiguration of accelerated RAN resources is applied in real time through a rule-based management. The micro-orchestrator presented in this demonstration is part of the Edge for AI Verge pillar. It supports the lifecycle management of FPGA SoC compute resources, thus contributing to sustainable computing goals. It also serves latency, energy efficiency, and reconfigurability KPIs. The goal of this demonstration is to build an end-to-end POC where the micro-orchestration concept could be showcased. In Verge, the micro-orchestrator is a component of the Edge Site Intelligent RAN Controller. The real-life implementation of the micro-orchestrator adopts the ORAN specifications and takes the form of two XApps. By accessing the resource usage forecast from an RApp regarding the total G-node B PRB utilization, RAN control actions can be applied at different control loop scales. Bubble RAN testbed equipment. 6 servers. ORAN front hall switch. 2 ORAN radio units. 6 Quectel 5G modems. RF shielding for over-the-air test and measurement campaigns. Kubernetes cluster artifacts. 5G core network. Open air interface and Open 5GS. G-node B. Open air interface and SRS RAN. Flex RIC. Observability layer. Prometheus, MySQL, Kepler, and Grafana. SMO layer with a non-real-time RIC and command line interface. For the dataset production, we deployed a bare metal setup of the open air interface. We fed this setup with a traffic pattern that provides a specific shape profile to the APERF3 data flow, and then by engaging the KPM XApp, we captured a time series dataset for 5 weeks. A stacked LSTM is employed, given the focus on multi-step forecasting. Also, multivariate input and attention mechanisms are considered, which align with complex temporal dependencies in cloud workloads. The key model architecture and training details are shown in the screen. After retraining the model, we obtained satisfactory results when comparing the actual data with the predicted one derived by the inference of the LSTM model. MQTT is leveraged to serve different endpoints, both internal and external to our demonstrator. The metrics of the data collection XApps along with the forecasts of the RApp are written to the database. The RAN control XApps read the forecasts from the database and apply policies in different control cycles. From the one hand, the slicing XApp regulates the PRB allocation per slice, non-real-time policy. From the other hand, the RU's FPGA SoC function reconfiguration XApp, part of the micro-orchestrator, applies adaptive function scaling and migration through a real-time control loop. A key component of the RAN control mechanism applied in Demonstration 2.3 is the rule-based policy framework. The latter has 2 branches. The first defines the PRB allocation per slice, whereas the second the type of function reconfiguration to be applied in the FPGA SoC device. The RAN control decisions are driven by the LSTM model PRB usage forecasting. The profiles of the policies to be applied are mapped to 4 time zones. For the FPGA SoC function reconfiguration, the microorchestrator is able to leverage a resource management layer that is able to scale a function or migrate it from one processing element of the FPGA SoC device to another. For example, from an ARM A53 microprocessor to the programmable logic area, and vice versa. This functionality was initially validated by using context events instead of the PRB usage forecast. To do so, a smart camera computer vision application drives the reconfiguration decision of the FPGA SoC resource management layer, which scales and migrates an FFT function in real time based on the number of detected faces. KPIs like execution time of the FFT function and also power consumption of the different FPGA SoC components involved in the function reconfiguration process are monitored and shown in Python dashboard. The performance metrics in terms of execution time and power consumption when the microorchestrator leverages the FPGA SoC resource management layer are shown on screen. To showcase the slicing RAN control action of the microorchestrator, we deployed a network in the Kubernetes cluster through a YAML file configuring the OAI 5G core network, the OAI Gnode B, the ARFSIM, two OAI UEs, the FlexRIC, the Monitoring XApp, the Slicing XApp, and the MySQL database. The Slicing XApp was designed to increase PRB resources in Slice A, while at the same time, decrease at the same proportion PRB resources in Slice B, and then vice versa. The energy footprint per slice is visualized through a Kepler exporter that is able to monitor the energy consumption of each pod in the Kubernetes cluster.